So we're coming to the final speaker of this session. Just 2 lines on Chris. He is Jerome B. Cohen, Professor of Material Science and Engineering. He is professor at the Northwestern University. And I added that he is the initiator and the director of the OQMD database. And so we are very happy, Chris, that you are here, and we are looking forward to hear about the implementation of FAIR data principles in the OQMD. And I stop sharing, and the floor is yours, please.
Okay. All right. Well, thank you very much. As you can see from the title of my talk, I'm going to tell you a little bit about OQMD. I think many in the audience have probably heard me talk about OQMD many times. So I am going to show you some kind of examples of things that we've done with the data in OQMD, but I don't intend to spend a lot of time belaboring that. I really want to spend some time talking about things that we've done in the past and things that we're doing currently to try and implement FAIR data principles within OQMD. I should start, of course, by acknowledging the people who did the work, both kind of current and former grad students in the group that are acknowledged here. In particular, I want to acknowledge Abhi Gopalkumar, who really did a lot of work in the kind of FAIR data things that I'm going to be talking about. And I think some of you know him from his work in Optim as well. Okay. So OQMD, so first of all, I guess I should say it stands for Open Quantum Materials Database, and it's essentially a large-scale database of DFT calculated properties. It's got both known, experimentally known, and hypothetical inorganic crystalline solids in the database. The known compounds come largely, the structures come largely from the ICSD. We have approximately about 50,000 of those. And then this is supplemented by a large number of what I call hypothetical solids as well, that were just essentially made up for some project or another along the way. I list here on the slide 800,000. We're just about to release a new sort of load of the OQMD data. And so we're going to be over 1 million compounds very soon. Since the beginning of OQMD, as you're going to see in this talk, the data has always been open, online, freely available. There's sort of no login required, no registration. You literally just come to the website and click. And there's a lot of things that you can do with data, as you've heard about in this workshop already. There's many sort of functionalities that you can explore, and in the OQMD database, there's a lot of these kind of functionalities. The one that I always kind of highlight, because I think I use it more often than anything else, is the automatic computation of convex hull information and phase stability. Okay. Yeah, I guess I should also say that I don't have it on this, but that the sort of privacy of the user is also kind of the openness of the data, and the privacy of the user is an important aspect of OQMD. So we don't, like I say, we don't require any kind of login information. We certainly don't do any kind of mining of the search histories and things like that. So really, this is just an open resource of data. Okay, so one thing that probably doesn't surprise you is that all of these databases are growing as a function of time. And so whenever you sort of quote any kind of data from the database, you always have to kind of give a snapshot of what year or what time period this was done in. And so I'm going to show you some data here just from a couple of years ago. If we sort of divide the compounds in the database into the ones that are on the convex hull and the ones that are not, if we just look at the stable compounds or the ones that are on the convex hull, we can sort of see in this plot kind of how many of them come from experimentally observed compounds. Sorry, that would be in the ICSD. And then how many of them come from these hypothetical compounds that we invented along the way. And this is given as a function of kind of the number of atoms in the structure. And you see that, for the low, the small unit cell structures, we actually have quite a few of these hypothetical compounds that are actually stable. Far fewer of them for the large unit cells, but the reason for this is that we just don't do as many of these hypothetical calculations for large unit cells. So the majority of the hypothetical calculations we've done have been for small unit cells. So I think there's every reason to expect that these numbers would grow if you simply investigated more large unit cells. You can also, of course, look at things like how is this divided into metals and insulators. So this is kind of the same type of information, but plotted as a function of band gap. You see the metals here and insulators with various band gap sizes. And again, you can kind of see a lot of hypothetical intermetallics have been found in our database. Again, this is mostly just because this is what we actually have spent a lot of time looking at. And we've spent less time looking at semiconductors and high band gap insulators. Okay, but this was some stats from a couple of years ago. If we look at a little bit more recent information about this, we can see again, kind of looking at the database itself and how many stable materials there are in the database. Right now, we're up to about 40,000 compounds that are on the convex hull out of this roughly a million or so materials. And you can kind of see how they're broken down in terms of metals and non-metals, the ones that are from the ICSD and the ones that are from high throughput hypothetical calculations. I guess the one thing that I find interesting about this that I'll point out is that you can see the number of hypothetical stable compounds is actually growing very quickly. The number of experimentally observed compounds is a little bit stagnant because basically these are, we mostly have exhausted the ICSD. So we know the compounds that we have in that database. And so what this has meant for us is that in the past, in the fairly recent past, the number of hypothetical stable compounds has actually superseded the number of experimentally observed stable compounds. So we actually have sort of more predicted stable compounds in the OQMD now than we have experimentally observed stable compounds. And so what that means is that I think the vision or the way we describe OQMD, I guess, has changed. I think initially we thought of OQMD when it first came online as a repository for properties of experimentally observed phases. And so it sort of started with the ICSD structures in that regard. And it's very quickly becoming a repository of computationally predicted phases in the sense that these are, these numbers are growing quite dramatically with time. Okay. So OQMD is indexed in search engines like Google. You can see here some stats about the coverage and the clicks and impressions and things like that. Yes. Okay. So just an example to kind of show you the types of data that you can get by doing queries at the OQMD website. You can search for compositions, like, for example, if you search for Al2O3 as a composition, I know you probably can't see all of the information on this slide, but that's okay. Basically, what you find is, the database returns that, yes, there is a stable phase with this composition. Here's the enthalpy of that phase, the decomposition into the sort of closest competing products. If there's an experimental formation energy, it's listed here as well, and so forth. And you see down at the bottom here, I know you can't see the details, but down at the bottom, basically, this gives all the polymorphs of Al2O3 that are contained in the database. And so you can select any of these that you might be interested in, and you would see then a page like this, where you see picture of the crystal structure, again, formation enthalpy, other information, like, for example, band gap, which is given here, heat of formation. If there's an experimental value, that's given, and the reference to the crystal structure. So the original reference to the crystal structure. And I sort of point this out as a little bit of an insider tip that, something that we know and use all the time in our group, but maybe isn't advertised on the website, is that generally speaking, if there's a reference to the data, this means the data came from ICSD. And if there's no reference to the data, it generally means it was a hypothetical high throughput predicted phase. So you can see down here at the bottom, there are some phases that have no reference and some phases that have a reference. So you can tell at a glance that some of these are hypothetically predicted and some of these are experimentally observed. We are, by the way, actually working to incorporate references to our high throughput predictions as well, but at the moment, the references are only to experimentally observed phases. Okay, so how do you use data like this? Well, again, there's many different ways. Many in the audience here know very well how to do these kind of things. I think one of the kind of earliest paradigms of doing these kind of using this kind of data was in what I call the direct approach to searching, where we basically do high throughput computational screening. The generic idea of this is quite simple. You start out with a very, very large number of candidates, candidate compounds, and then you devise a set of progressively restrictive screens that you can essentially use to knock candidates off the list. So if you start with a very large list and then you say for the application I'm interested in, the candidate has to have all of these attributes, and you screen for all of them. And the idea is that at the bottom of the screen, you have a small number of candidates that fulfill all of these screening conditions. Okay, so just to show an example of this is admittedly kind of an old example, but I think it actually is a nice illustration and actually shows some FAIR data principles as well. I'll explain in just a minute. This is a very early study we did where we were looking for precipitate strengtheners in BCC metals, and we particularly were looking for Heusler phase crystal structures. So to search for these, we basically just took the Heusler phase ternary crystal structure. We decorated it with essentially all possible elements in the periodic table, not quite all, but most. And then did calculations of those, turns out to be about 180,000 Heusler phases. Okay, so this plot here, sorry, the y-axis looks like it's a little bit cut off, but this plot essentially shows a plot of the stability of this phase. Basically below 0 on this plot means the compound is on the convex hull. Above 0 means it's not on the convex hull. And this is plotted as a function of lattice parameter. And so you can see that if you look at this cloud of points, that the vast majority of these phases are above the line, meaning if you do 180,000 calculations of these kind of at random, the vast majority of the time you're going to find unstable phases. Maybe not too surprisingly, right? We're just throwing darts at the periodic table and we don't find stable compounds that often. But maybe surprisingly, given the fact that this is so simple, is that you do actually find stable compounds, and you find actually quite a few of them, even with this very simple approach. Okay, so the idea for the precipitate strengthener was simple. We basically said, okay, we want to find something that's kind of low on this plot so that it would be more stable, hopefully below 0, but maybe even a little bit above 0 would be okay, but somewhere low on the plot. We want the point to be dark red. I didn't tell you what the color meant. The color here is basically a very simplistic estimate of the cost based on just the elemental production of the elements that go into the compound. But this is not really important for today. Just basically red means cheap and blue means expensive. So you want red if you're looking for something that's going to strengthen iron, for example, that's relatively cheap. And then for sort of metallurgical reasons, you might want the precipitate to have a lattice parameter matched to the host matrix. Like in this case, we were looking for a strengthener for BCC iron. So you might take the BCC lattice parameter and look for something close to that. Okay, so this is a very simple kind of visual screen. And the basic idea is you would look in this region of the plot for something that's red. And that's kind of how you could use that to screen this large set of data to look for precipitate strengtheners. And I should say this approach was quite successful. We actually found essentially all of the known Heusler phase strengtheners for BCC iron, and in fact found some new ones as well with this approach. Okay, So like I say, kind of an old example, but I just wanted to illustrate that because I thought that this illustrated some of the reusable principles of FAIR, in the sense that at the same time, I had another postdoc in my group who was interested in thermoelectrics, and he said, look, I don't care at all about precipitate phases and these Heusler precipitates, but he used essentially exactly the same data set to try and find new thermoelectric materials. So he took exactly the same Heusler data set and looked for compounds in the data set that were semiconducting, that had a gap of a certain size. And in addition to kind of the, some of the well-known Heusler compounds, found some new ones that were previously unknown, okay, containing things like barium, gold, and antimony. And those were interesting then, because when we looked at the electronic structure of those compounds, they looked quite interesting from a thermoelectric point of view, and they motivated us to do phonon calculations. And those also looked interesting from a thermal conductivity point of view. They had these very sort of low-lying acoustic modes that suggested a kind of almost rattling type behavior of some of the atoms in the Heusler phase. And indeed, we called these materials rattling Heuslers or R Heuslers, and then went on to do thermal conductivity calculations and found that they had extraordinarily low thermal conductivities, and hence predicted very high values of the thermoelectric figure of merit CT. Okay, so I really, again, didn't want to get into thermoelectrics, but just wanted to illustrate this because I thought this was an interesting example of how the data can be reused for a completely different purpose. And of course, that can only be achieved through incorporating things like FAIR data principles. All right, one other example comes in the area of machine learning. So, the problem with this kind of high throughput screening and just looking through the data set for compounds that we're interested in is, as you saw in Stefano's talk just before, that as you sort of increase the number of elements in these compounds, if you take this kind of high throughput screening approach of just saying, okay, I'm just going to permute all possible elements into that structure and just calculate all the permutations, obviously that doesn't work anymore as you sort of increase the number of elements in the compound. So once you get up to quaternary or quinary compounds, the number of possible permutations becomes extraordinarily large. And so we can't take this kind of brute force approach anymore. We have to take something a little bit more efficient than that. And machine learning provides us a way to do that. These machine learning models can be trained on large data sets, but again, are sort of reliant on the idea of large scale training data being available. And again, I think the FAIR principles are kind of a good provide us a good guidance for how to make this data accessible and useful in machine learning models. So again, we've spent a lot of time over the past years sort of training these models, sort of coming up with new representations for training the ML models. But the generic idea of these things is that if you can use a large data set like OQMD to train a machine learning model, actually use the machine learning model to explore these extraordinarily large combinatorial spaces that you can't explore with just high throughput DFT. So one example of that is that we can actually use machine learning to accelerate the high throughput DFT searches themselves. So this is just an example of showing a high throughput search for a quaternary compound, pasylite or double perovskite structure. It's again sort of one of these compounds that's compositionally complex enough that we just can't enumerate every possible combination and do a calculation from DFT. So instead, what we do is we basically train a machine learning formation energy model using the entries of OQMD. Then we use this machine learning model to actually generate a very large number of possible prototype compounds by decorating elements into this structure type. In this case, we we construct about 1.5 million possible compounds. And then we use our machine learning model to predict the energy of all these compounds and basically look for cases where machine learning is predicting that the energy of the compound should be relatively low compared to the DFT convex hull that we have in OQMD. So we're looking for cases where machine learning is telling us there should be something low in energy there. And then we basically just sort this list and take, say, in this case, I think we took the top 5,000 in this list. And we just do DFT calculations of those top candidates predicted by machine learning. In this particular case, we discovered about 1,000 new stable compounds by doing only 5,000 DFT calculations. So roughly a hit rate of about 20%. A hit rate of 20% is sort of extraordinarily large. This is about 150 times more stable compounds than you would get by just doing this kind of undirected search where you just enumerate everything. And so you can kind of see how this can accelerate these searches. And I don't have it on this slide, but you can also see very clearly that once you have data from these 5,000 compounds, you can actually feed this back into the machine learning model and retrain a new generation and repeat the process. And you can kind of do this in an iterative way to find compounds much, much more efficient. Okay, I guess another thing that I maybe should mention about the machine learning aspect of this is that a lot of these hypothetical compounds that we've generated along the way admittedly are very high in energy, because again, we're just kind of throwing darts at the periodic table. So we have a lot of very kind of high energy, chemically unreasonable compounds. It turns out that these compounds are extraordinarily important for training machine learning models, right? We have to have good positive data and good negative data to train these machine learning models. We didn't realize that at first, I guess, and we started by training machine learning models to have stability, and we only trained it on stable compounds. Well, of course, if you do that, the machine learns very quickly that everything is stable because you only trained me on stable compounds. So you obviously have to have negative examples too, and these kind of hypothetical high throughput DFT surveys actually have provided us with a lot of extra data. Okay, and then the final example is that we've recently been doing a lot of work in sort of applying ideas of network theory to these data sets. These convex hulls kind of naturally lead themselves to a network construction. Convex hull is really just a series of points, the compounds that are on the hull, and lines connecting, the tie lines connecting phases in the convex hull. And that sort of naturally leads itself to the idea of constructing a network. If you think about constructing the entire network of the entirety of the OQMD then, or the convex hull of the entirety of OQMD, this would be like a convex hull of an n component system where n is the number of elements in the periodic table, right? If I imagine, not just constructing a binary or a ternary or a quaternary convex hull, but a 100 component convex hull, then the interesting thing about that is that there's only one of these convex hulls. There's, this convex hull of everything, there's only one. And every sort of binary and ternary and quaternary is just a slice through this very high dimensional object, right? If we have a 100 component convex hull, basically this is a 100 dimensional object. So it's very difficult to visualize, but possible to calculate. So we have calculated that, that sort of one convex hull to rule them all in some respects. And we can analyze the topology of that in terms of the number of stable phases, the number of tie lines. It turns out there's about 40 million tie lines in this convex hull. When you analyze the topology of this network, you see sort of dramatic differences between this materials network and social networks and things that network theory people have spent a lot of time studying. It's a very, very highly connected, dense network. There's a large number of tie lines coming out of every node on average, about 4,000, meaning on average, every inorganic compound can form a stable two-phase mixture with about 4,000 other compounds. The rest of them would react to form something else, and so forth. I could spend a long time talking about the topology of this network, but this is one of the areas that we've been exploring as of late. Okay. So I want to turn to the FAIR data principles, which is what I said I was going to talk about in this talk. I obviously don't have to go over these principles with this audience. You understand that quite well, but just to kind of briefly reiterate some of these ideas that I think were originated in this paper in 2016. You know, the findable idea is obviously to use data or to reuse it. You first have to be able to find it. For that, we want some kind of globally unique persistent identifiers, which I'll talk about. We want rich metadata, things like this. Next, you know, once you find the data, you have to be able to access it. So accessibility is quite important. It's important that the protocol for accessing the data be free and open. I'll talk about that as well. Interoperability, the data needs to be able to sort of be interoperable with other data, with other applications and workflows. You know, for this, we need the metadata to be available, and the metadata itself should follow FAIR principles. And reusability, of course, is the ultimate goal, I guess, of these kind of principles, that we want the data to be sort of reusable in a large number of different applications. And I tried to show you one example. Okay, so let me show this timeline of some of the FAIR data principles in the OQMD. Even within my group, I have to say it's a little bit controversial about when OQMD exactly started. Somewhere around 2012, 2013. I guess the first time we actually published a paper on it was 2013, so that's as good a date as any. Even at the beginning, as you can tell from the very first letter of the first acronym is being open. From the very beginning of OQMD, we were sort of focused on making sure that this was an open repository of data, freely available. Already at the beginning, you know, you could do compositional queries. You could always download the database with essentially 1 or 2 clicks. That was sort of always a functionality of the data. It has not changed and was always there. QMPy was sort of open sourced and put on GitHub a year later. In fact, QMPy was actually available before it was on GitHub, but in a maybe less convenient form. So this is as good a timeline as any. Okay, then you see the FAIR data article, and then here I have the Optimade RESTful API that you probably heard a lot about in this workshop already. That's come out recently. The paper has come out recently. The API was available a couple of years ago, and OQMD is participating in that, I think, very important endeavor as well. And then I'll show you some examples of how we're more recently we've tried to incorporate properties of structured data within OQMD using schema.org, and then again more recently incorporated persistent identifiers into the OQMD data through Handle. Okay, so some of the kind of again, what students in my group now call old school OQMD, the pre-2016, you know, again, that initially the QMPy API and framework was always available, and there was a full database download available, you know, from the very beginning. This kind of incorporated all of the aspects of FAIR. You could query the data by either entry or compositions that I tried to show you screenshots of earlier through various URLs. And this made the data sort of more findable and accessible. And this was accessed by an open CC by 4 license, again, kind of from the very beginning. Okay, so that's kind of the starting point of OQMD. Let me just go through each one of those a little bit very quickly on its own slide. That again, sort of initially downloading the full OQMD was always available. You could always kind of post your own copy of this locally if you wanted to. So you could download the entire database and the API via this kind of very simple download URL, download the QMPy API through GitHub, and install. So I don't know how many people actually did this. I know some did, but you know, if you didn't want to if you didn't want to sort of rely on the web interface or other things, you know, you wanted to do kind of larger searching yourself, this was the way you could do that initially within OQMD. The URLs, like I say, were sort of organized in such a way that that you could access various entries. If you knew the OQMD ID, they were sort of organized in terms of the various entries. Compositions were sort of organized by chemical formula with these kind of URLs as well. You know, these were all of the information was returned with an HTML format from this. So you know, this was maybe not the most convenient way for people to do like kind of large scale searching, and it would require you to actually, you know, use some kind of program to interpret the data. But this was kind of an early attempt on our part, I guess, to be fair at that time. Okay, so what about the more recent things, the post 2016? So again, like I said, there's sort of three main things I want to talk about. The Optimade RESTful API. Maybe I don't really need to talk about this so much because I have a feeling that others can probably talk about it much more eloquently than I can. But I'll tell you just briefly about that, about the OQMD incorporation of that, and as well as persistent identifiers and structured data. Okay. So again, the RESTful queries now that you can do with Optimade, again, this audience probably understands quite well the difference between these APIs and RESTful APIs. So we want the query to be stateless, to be sort of all the queries to be independent and not depend on the cache state of the system and so forth. And Optimade, I think, has done really a very nice job of doing that and making a lot of the data in the various repositories interoperable. And I just wanted to sort of point out that there's a few OQMD authors on this original Optimade paper. So we're definitely very much in support of this idea and moving this forward in the future as well. Again, I think people have talked probably about queries from Optimade. You can do these kind of very simple queries very directly. You get sort of a JSON structured list of the data that's returned. So in a very convenient format. You know, just to say, I think that this is really something that's quite helpful, and we're already kind of starting to use it and in our group as well. In addition to JSON, we support the XML and YAML formats as well. The user interface can be anything essentially with HTTP, like a web browser or other things. And there's, you know, sort of powerful metadata that goes into these. And here's some links of the Optimade endpoints that are included in the OQMD website. Okay. Oh, one other thing that I guess this was not sort of required, but just to say that we actually include the Django query that's executed on the MySQL database in the metadata as well, just in case that some find that useful. Okay, so let me tell you what we've been doing with the persistent identifiers. So again, many of you probably know persistent identifiers are essentially just a long-lasting digital reference to an object. For example, a web URL can be a digital reference. The long-lasting part of this is key because the web URLs can change, of course, and so you wind up with this problem of link rot, where if you sort of change URLs in a database, but the system is not updated, then lots of links can be broken and don't work anymore after some period of time. Okay, basically the bottom line is that it takes time and money to actually keep the legs active. And so having these in some long-lasting format is quite useful. And so you know about many examples of these persistent identifiers already, DOIs and ORCID ID and ISBN. These are all examples of persistent identifiers. And the problem, of course, you can imagine is for a URL like this from OQMD that points to a particular entry, you might imagine at some point in the future, maybe we make a new version of OQMD, and so we want to have version 1 in the URL. Or maybe OQMD expands beyond materials to other things, and so we want to have a materials qualifier in the URL, or outside of Northwestern, so we want to incorporate that, or other things like that. So any of these things would sort of cause us problems in terms of this URL, and so if we had a persistent identifier that could point to the original entry, this would be quite useful. Okay. So we've been doing this through handle.net, which is part of CNRI, which I have to admit, I forget what the acronym stands for exactly right now, but it's okay. But basically this provides us with a unique persistent identifier associated with each entry into the OQMD, and you can see kind of the format of that. It's given a unique number here, which is generated by handle. And then the format here is OQMD is the first part of this string, version 1 corresponding to the version of OQMD. EN means entry. This is an entry page. And then the OQMD ID. And then version 1 just, again, sort of pointing to the version of this entry. That could change. Okay, so we have now these persistent identifiers for each entry on the OQMD website, and the way queries are handled is illustrated here. That sort of when a query comes in from a user's local browser, the handle.net central server sort of passes this to a dedicated handle server we have, which then passes this on to OQMD.org. So it's a little bit complicated in terms of this process, but then the OQMD.org is able to directly give the HTML response to the user's local browser. It doesn't have to go back up this chain back to the user. And I guess I have on my first slide here, these persistent identifiers, I think, are quite important, but they're not magic, right? They don't sort of magically remain persistent. It's still the responsibility of the database maintainers to keep them active and to redirect the correct pages. So right now, we're still managing these at Northwestern and are making sure that these IDs point to the correct pages each time we update the database. Okay, and then finally, the issue of structured data. Structured data is just basically a structured summary of page content. It's widely used by search engines. You probably use structured data all the time when you do Google searches. Schema.org is a collaborative effort that's sort of made a lot of inroads in this area. It's a collaborative effort of some of the biggest search engines in the world, and it's really developed by an open community process. So Abi, my student, made this illustration of cheesecake recipes. He said, if you search Google for cheesecake recipes, today you might find a response that looks like this. In the old days of Google, if you did this search, you would just find a list of links of different websites that you might go to for cheesecake recipes. But now you get this much more useful, formatted and kind of beautiful, clean illustration of different websites. And you can see, each of them has a nice picture and shows the rating that people have given to that, and maybe even the time it takes to make a cheesecake. Wow, does it really take 10 hours to make a cheesecake? I had no idea. Anyway, but the idea is that because the data on these web pages is structured in the right way, then the search engine can actually do this, pull out this information and show it to you in a kind of much more clean and useful format. So the question is, how can we use this kind of structured data or incorporate this into materials database repositories? Oh, sorry. One other thing is that, if you following through with this example, if you went to any one of these websites, you might find a whole bunch of text with the author of the website talking about the cheesecake. But then somewhere below the text, you might actually see a nice little box like this, which kind of summarizes things for you and is even maybe in a printable form. So again, this is kind of a nice way that structured data can be used to kind of streamline the websites and make put the data in a much more useful format.
Chris, so, can you wrap up because we are running out of time?
Okay. Yep. I think this is my last slide. So basically, just to say that we've sort of been trying to incorporate some of these concepts, and just to show you from the data set search from Google, if you search for something like AL203, you actually do see some structured data hits from the various repositories here. Maybe not quite as beautiful yet as the cheesecake recipes, but I think we're sort of moving in the right direction here. And this is just a list of some of the different types of structured data that we have supported currently in OQMD. Okay, and I think, ideally, maybe at some point in the future, if we really get this structured data right, you can imagine talking to your Google Home or Alexa and asking them queries about materials data like this. Okay, so I will stop there and take any questions. Thanks a lot.
Okay, thank you very much, Chris. So questions to the audience in Louvain or to other people? Maybe I start with one in terms of this FAIR, and in terms of what we discussed this morning when you were still actually in bed, hopefully. So that was reproducibility or accuracy and precision. So in particular, if you use a database for something where the data were not produced for, but you want to do something else, right? The reusable, or what we call repurposable, you also want to know the accuracy for this other application. So how much information about accuracy, and that means about basis sets, exchange correlation functional, and other details, is really available?
Yeah, that's a good question. I mean, I guess in some level, the answer is not too much. As you very well understand, that in constructing a high throughput database like this, you essentially have to make choices for all of those, those input parameters. And the choices are made kind of with the idea of economies of scale, right? You want the data to be as converged as you can get for as cheap a computational expense as possible. But then once you make those choices, you kind of have to freeze them and generate all the data with a constant set of these parameters. So yeah, it's entirely possible that, for somebody who's really interested in some very subtle property that requires much higher level of convergence than what we've done, that our data just wouldn't be accurate enough. But we don't really have any way of sort of, other than giving the parameters of the input file, which we do give, of course. Other than giving that, we don't sort of give any instructions to the user about, yeah, you're really trying to use this for a purpose for which it was not designed. Yeah,
I mean, that's why I really say the input data would be really important, right? If you really use it for something very different, to make sure that you're not running into something wrong, people probably have to estimate the accuracy or precision themselves.
I suppose, yeah. I mean, yeah. Well, for sure, like you say, the best thing you can do is to provide all the information, right? And that we provide. But that information itself has to, there's some expertise required to determine whether that information is useful or needs to be supplemented.
Mm-hmm. Okay. Other questions?
I don't know if I'm allowed to ask a question, but I would say I would be interested in, Stefano or other database people, if they have a better response to that question.
I think actually let's come back to this in a moment when the three of
Okay.
us really discuss exactly maybe
Okay.
this point.
Okay.
So it's a good thing to start with, I think. Yeah.
Okay.
I think there was a question from Louvain, if I understood correctly.
Yeah. Maybe not directly related to the FAIR principles, but maybe a bit broader. You mentioned the existence of materials, but to what extent is it also then possible to extend this with properties? I mean, from the Huisler alloys, you mentioned the thermoelectric properties. For the manganese Huisler alloys, they are very well-known ferromagnets. To what extent can you expand this with various properties, elastic constants, polarizabilities, and so on, and so on?
Yeah, I think in some sense that, you know, you can expand to kind of any property you want as long as you have sufficient human labor and sufficient CPU time. And so just naturally, we've kind of focused specifically on the properties that we're most interested in. You know, we haven't really necessarily made this database thinking, you know, we really want to cater to all users. But yeah, we are making some kind of attempts to expand to vibrational and thermal property data and some of the thermoelectric properties as well. But again, that's sort of mostly motivated by our own interests. It is entirely possible that you can include things like elastic constant data. Materials Project already has a lot of data like that, for example. We just haven't, so far, to be honest, seen a great need for that. To be quite honest, when we need that, we just use Materials Project. So yeah, I guess I would say in some sense, there's no problem doing that, but you have to have people to do it, computers to do it, and then you have to have kind of the interest to do it as well.